Hi, I'm here and I'm ready for our webinar today. Okay, today we have more or less 1 hour to talk about our theme, how to plan expression and affinity chromatography-based protein purification for structural analysis. As mentioned before, I'm Susan, application specialist at Lifesciences for protein production and assays. And during my studies and my PhD, I expressed and purified several proteins, for example, transcription factors, enzymes, or proteins with unknown function. And sometimes it wasn't very easy. And during this time, I learned a lot about protein expression and purification. And on these basis, I created these presentations. And these presentations should be a guideline for you. And I hope it will be helpful for your planning of your protein purification and affinity chromatography. So let's start. The aim of the webinar should be that you are able to make the right decisions regarding the expression host. So if you use yeast, E. coli, insect cells, or mammalian cells, regarding the buffer system. For example, if you use tris buffer, MOPS buffer, or sodium phosphate, and regarding the affinity tag. So if you take the HIS tag, the GST tag, flag tag, strap tag, and twin strap tag. And regarding the resin format, so if you take cartridges, magnetic beads, or gravity flow columns. Yeah, and to make the right decisions, you have to find the answers for 2 initial questions. So what are the properties of the protein? And the second one, what are the requirements for structural analysis? Depending on the existing knowledge, it is more or less easy to answer both questions. But if you take the time to answer them, the answers would be a great help for your planning steps for protein expression and purification. So let's start with the first question. What are the properties of the protein? Your protein has several properties. One of the properties which can be easily answered is from which organism the target protein originates. That could be, for example, soy bacterium, viruses, or mouse, or something else. Yeah, a second property that is combined with this first property is the localization. So where is your target protein localized within the organism, or more precisely within the cell? So if it is localized on the mitochondria, or it is localized on the membrane, it is a cytoplasmic protein, or somewhere else. So, and if you don't know the localization of the protein, you can use prediction tools with the help of the amino acid sequence of your target protein. And these prediction tools can also say if your protein has specific domains or signal sequences. Those specific domains or signal sequences could be, for example, a secretion signal, or membrane domains, or something like that. Yeah. And if you know if your protein contains specific domains or signal sequences, you can also get information about a protein class. So if it is a membrane protein, or a metalloprotein, or if it is an antibody. And the 2 last properties I want to focus on today are the isoelectric point and the size or molecular weight of the protein. And if you collect all this information, you're well prepared for your protein purification and expression, because the organism and signal sequences provide information which host you should use, and the isoelectric point, the localization, specific domains, and protein class are helpful to find the right buffer system. And specific domains, the protein class, as well as size or molecular weight and signal sequences provide information about the perfect tag and the resin. Yeah, so in the next slides, I will focus on each circle, and we will start with the first circle, the expression host. The most commonly used expression hosts are E. coli, yeast cells, mammalian cells, and insect cells. E. coli is a prokaryotic host, and yeast cells, mammalian cells, and insect cells are eukaryotic hosts. Advantages of E. coli are that they're easy to handle, they grow really fast, you need no special equipment, and therefore E. coli cells are very economical like yeast cells, because they also grow really fast and you do not need special equipment. But disadvantages of E. coli as expression host for eukaryotic proteins, so if they proteins are from yeast or mammalian or insect cells, are that E. coli does not contain a machinery for splicing, so you have to use a coding sequence without introns, and E. coli has a different codon usage compared to the eukaryotic hosts. And a further disadvantage of E. coli is that E. coli does not contain, or that there are no post-translational modifications are possible. So, for example, you will not get a glycosylated protein after the expression in E. coli. And the sample after the preparation contains endotoxins, which could be a drawback depending on the subsequent application. And if the protein is highly expressed in E. coli, degradation or inclusion bodies are possible. Compared to E. coli, yeast cells, mammalian cells, and insect cells have these post-translational modifications, and the sample do not contain endotoxins. But like E. coli, yeast cells have disadvantages. For example, the codon usage is as well different compared to mammalian cells or insect cells, or the higher eukaryotes. And sometimes proteins which are glycosylated are hyperglycosylated. And if you have a protein that should be secreted, we would not recommend to use yeast cells, because sometimes the secretion is really inefficient. Compared to yeast cells, mammalian cells and insect cells have these proper folding or this right glycosylation profile. But drawbacks compared to the other expression hosts are that you need special equipment, and you have to know how to handle them. And these complicated culture conditions raise the costs for the expression in mammalian cells and insect cells. And there is the possibility that you can get contaminations with animal viruses. And for insects, there's also the problem that they not continuously express the protein. So you have to transform from time to time the insect that's new. Yeah, so the take-home message for the selection of the expression host is choose a host that is similar to the original organism and consider signal sequences. So we are at the end of the first circle about how to find the right expression host, and now we can go on with the second circle, how to find the right buffer conditions. Yeah, at the beginning, I mentioned it is necessary to know the isoelectric point of your protein. So the isoelectric point, or in short, the PE, is the pH at which a molecule carries no net electrical charge or is electrically neutral. That means if the PE says or give information if your protein is soluble at a specific pH or not. So if the pH is equal, the pH of the buffer system is equal to the PE of the protein is denatured. If the pH of your buffer system is below the PE of your target protein, your protein is natively folded, but positively charged. And if your buffer system has a pH lower, higher than the PE of the target protein, your target protein is natively folded and negatively charged. So the buffer should have a pH below or above of the target the PE of the target protein. Then you have a natively folded protein. Yeah, and if you know the PE or the PA ranges which are possible for your protein, you can select the right buffer system. A commonly used buffer system is a Tris buffer. It has a PA range from 7 to 9. But if you need a buffer system with an acidic pH, you can use, for example, sodium acide, mass buffer, sodium phosphate, MAPS buffer, or something else. And if you need a basic pH, then you can choose one of the lower ones, for example, Herbst, Tricin, sodium tetraborate, or Biceno or glycine. And if you have selected the right buffer system, you can think about additives. What are additives, or which information do you need to select the additives? You need the information about the localization, the protein class, and specific domains. These information could be, for example, if you have a metalloprotein. Metalloproteins have a metal binding site, for example, for calcium or zinc or manganese. And these metal ions are necessary to stabilize your protein. It is also possible that your protein has a ATP or a GTP binding site, and then you have to add ATP or GTP to stabilize your protein. A further additive are reducing agents or metal chelators. So if you have a cytoplasmic protein with cysteines, then you have to add DDT or beta-mercaptoethanol, because cysteines or proteins with cysteines in the cytoplasm normally do not form disulfide bonds. And to prevent the formation of disulfide bonds in the cytoplasm or during the lysing of the cell, you have to add DTT or these reducing agents to prevent the unnatural formation of disulfide bonds. A lot of proteins have also protease recognition sites. And if you lyse your cells, then these proteases could be very active and cleave your protein. And in this case, you have to add metal chelators like EDTA or EGTA. These metal chelators can bind metal ions, for example, calcium or manganese, or the metal ions which are necessary that to have a active protease. And if you add these EDTA or EGTA, the metals are bound and the proteases are inactive, and your protein will not cleave. And if your protein is a membrane protein, then you should add agents for solubilization, or in other words, detergents. And these detergents could be SDS or Triton. And these detergents will help you to dissolve your protein and to get it out of the membrane. So now we have focused on the second circle to find the right buffer system. And now we can go over to the last circle, finding the right tag and the resin. Yeah. To find the right tag and resin, you need information about domains and signal sequences. This picture shows only membrane proteins, but for me it says more than 1,000 words. So your protein could have a membrane domain, or you can have a protein which is partially secreted via the N terminus, or you have a protein which is partially secreted via the C terminus. And due to the secretion, or during the secretion, the signal sequence which is at the N terminus or at the C terminus will cleave off. That means if you place your tag at this side or this side, you will lose your tag during the translocation of the protein. So it is better to place the tag not after the signal sequence or at the other end of the protein. And some proteins have several membrane domains, and it is not recommendable to place the affinity tag within such a membrane domain. And some proteins interact with other proteins, and you should know these interaction sites, because if you want to have a functional protein, these interaction sites should not contain the affinity tag. And some proteins also have post-translational modifications, and these sites should also not be influenced by the tag. Yeah, so you should keep in mind signal sequences and specific domains to if you select the optimal position of the tag. Yeah, and the selection of the tag and the affinity resin is also influenced by the size or molecular weight of the target protein. And with this slide, I want to explain why the size or molecular weight of the target protein influences the affinity chromatography resin. Because normally or mostly the affinity chromatography resin consists of agarose beads, and these agarose beads have a 6% concentrated agarose. And due to this high concentration of agarose, the pores of the agarose are, I will use the pen, are really small. So small proteins can enter the agarose beads, you can see, but the large proteins will not enter the agarose bead. So normally your agarose bead is coated with the binding sites for your tagged protein, and the small proteins can find binding sites within the bead because they can enter the agarose bead, and large proteins will only find binding sites at the surface of the bead. So that means you have more binding sites for small proteins as for large proteins. And therefore you have a lower binding capacity for large proteins with a 6% agarose bead. So that means you will have a normal yield with small proteins, but if you have a large protein, a 6% agarose will lead to a lower yield. To prevent this, I would recommend to use a 4% agarose, because these 4% agarose has larger pores. So as well as small proteins, as well as large proteins can enter the agarose. And both the small and the large proteins can find binding sites within the agarose bead and binding sites at the surface of the agarose bead. So you have a high binding capacity for small proteins and for large proteins. So with the 4% agarose, you can easily purify with a high yield small and large proteins. So I would recommend you use a 4% agarose. You're every time on the safe side, and you will have a high yield for small and large proteins. Yeah, now we have finished the last circle, the tag, also to find the tag and the resin, but the selection of the tag and the resin is also influenced by our second question. What are the requirements for structural analysis? Conventional methods for structural analysis are cryo-EM, X-ray crystallography, and NMR. Today, I will not focus on these methods in detail because our hosts for today are the expert in this case, but I will focus on the at the requirements which are similar for these three methods, because for structural analysis you need a tag which is really small, because only small tags can remain at the target protein, and if you have a large tag, this large tag has to be removed, because large tags will influence the structure or function of your target protein. A second requirement which has to be fulfilled are the amount. So you need mostly milligram of your protein for the analysis. And for structural analysis, you also need a high purity of your target protein, and it should be naturally folded. So I will compare conventional or the mostly used affinity tags if they fulfill these requirements I mentioned. And therefore, I will focus on the GST tag, the flag tag, the his tag, and the strap tag 2 drone strap tag. Now let's start with the GST tag. Yeah, the GST tag is one of the largest tags. It has a size of 26 kilodalton. And so the GST tag cannot remain at the target protein. You have to remove it with proteases, because these large tags will influence the structure or function of your target protein, and you will not get the wanted data. The amount you will get with the GST tag is really high. Mostly you will get 10 to 30 milligram per milliliter resin. The purity with the G tag is more or less medium. And as I mentioned for the first requirement, the proteins are mostly not naturally folded, and you can also not use the GST tag for proteins with disulfide bonds, because you need the reducing conditions and detergents cannot be added. And the GST tag can also only be connected to the C terminus of the target protein. And due to the large size, the protein structure is influenced. So if you plan structural analysis after your protein expression and purification, you should not take the GST tag. A further tag which could be possible is the flag tag. And now I will check if the requirements are fulfilled for the flag tag. The flag tag is a small tag. It has only a size of or a molecular weight of 1 kilodalton. But the amount you will get with the flag tag is really low, with only 0.5 to 3.5 milligram per milliliter resin. So if you purify several milligram with this resin, it would be very expensive. But the purity with the GST tag, with the flag tag, is really good. And but the problem concerning the folding is that the pH, if you work with a pH shift, the pH shift can influence the structure or function of the protein. So due to these disadvantages, I would not recommend the flag tag if you plan structural analysis afterwards. So now I will focus in more detail on the his tag. The his tag, as the flag tag, has a small size of 0.8 kilodalton, which is it's a bit smaller than the flag tag, and yeah, it's a really small tag. In principle, you can purify 5 to 40 milligram per milliliter resin. But the yield is only so high if you take or if you use E. coli as expression host. I think this picture is worth 1,000 words. Here you can see, or now I will explain the reason why the yield is only so high if you take E. coli as expression host. You can see here a purification of M. cherry. M. cherry is this pink fluorescent protein, And M-cherry was tagged with the his tag and purified with a conventional nickel anti-A resin. Normally, the tagged protein should bind on the upper part of the resin or of the column, so in this part. But here you can see that the protein do not bind in the upper part and flow through, and only bind in the lower part or do not bind. And if you add more protein will go to the lower part of the resin. And the reason for this is that mammalian media or media for insect cells often contain histidine or glutamine or arginine, which compete with the his tag for binding sites. So the resin is charged with nickel ions, and these nickel ions bind the free amino acids and not the his tag protein. And these linked or these free amino acids are the reason that the protein flow through or bind in the lower part. So, or in other words, the amino acids are similar to an eluent or to imidazole, and they wash the protein out of the column. So the amount is good if you take E. coli, but if you want to use mammalian cells or insect cells, the yield is lower as expected. The purity with the his tag is really low. An example is shown here. So if you tag M-cherry and GAP-DH were tagged with the his tag and purified with a conventional nickel anti-A resin. And at the or on the SDS page tail, you can see the flow through and 3 elution fraction for each protein. And besides the target protein and cherry and GAP-DH, there are several proteins more which are unspecifically bound by the resin, and also in the elution fractions. The reason for this is that, for example, proteins from mammalia or antibodies often contain natural histidine repeats, and proteins with natural histidine repeats will also bind to the nickel anti-A resin. So you will purify the his tag protein and proteins with natural histidine repeats. And they are all in your elution fraction. So you have to optimize the his tag based protein purification to use these to reduce these high unspecific background. Further purification steps are necessary to increase the purity. The protein purification with this tag is, as for all purification methods, divided in 4 purification steps. So the first is the equilibration of the resin, then the sample application. Afterwards, the resin is washed, and then you have the elution. During the wash and the elution, imidazole is added in different concentrations. So you have, for this optimization, you have to titrate the imidazole concentration for the wash fraction and elution fractions to separate the unspecific bound proteins from your target protein with the his tag. So for each protein, you have to find the perfect or optimal washing conditions and the optimal elution conditions. So that's the reason why the purity is really low, and you have to invest several hours to find the perfect purification conditions, or in the best case you can optimize them, but sometimes it is really difficult to find these optimal or purification conditions with a higher purity. And the last problem of the his tag is that you have also sometimes not naturally folded proteins depending on the properties of the protein, because reducing and chelating agents are not recommended, and tris and HAPs are also not recommended. So you cannot use these conventional buffer systems. Yeah, that means if you have a his tag protein, you cannot use reducing agents like DDT or TSAP. So if your protein is a cytoplasmic protein with cysteines, you should not use the his tag, because then you cannot act at the protection agents like DDT, because without DDT or a similar reaction, your protein with cysteines will be will form disulfide bonds, which are unnatural. And if your protein is prone to oxidation, you can also not protect them with DDT. And during the cell lysis, you will have the oxidation of your target protein. And a further drawback is that you cannot add chelating agents like EDTA or EGTA, because as I mentioned before, the resin is the nickel NTA resin is charged with nickel ions, and if your buffer contain EDTA or EGTA, the nickel ions are captured by EDTA and EGTA, and so you will reduce with EDTA and EGTA the binding capacity of the nickel NTA resin. But if you have a protein that is prone to proteolytic damage, then you need these EDTA or EGTA, and you have to add it. And but with the his tag based protein purification, EDTA and EGTA are not possible. And the last reactions which I would mention at this point are tris, HAPs, MOPs, and ammonium, which cannot be used for the his tag-based protein purification. And therefore you will have problems to find the perfect buffer system for your protein, especially when you have a pH sensitive protein. Yeah, and so the his tag, you would know, is not, I would not recommend it for if you plan structural analysis afterwards. So now we will focus on the strep tag and the twin strep tag, and if they can be used if you plan structural analysis afterwards. So the strep tag 2 and the twin strep tag are both small tags. The strep tag 2 has a size or a molecular weight of 1 kilodalton, and the strep tag 2, the twin strep tag, has a molecular weight of 2.8 kilodalton. The twin strep tag is the larger tag because it contains the strep tag 2 motif 2 times, and these both motifs are separated by a spacer sequence. And therefore, both tags have a different size. The amount that can be reached with streptactine or streptactine XT resin are 3 to 25 milligram per milliliter resin, which is quite good. And you can use the resin, or this amount can be achieved with E. coli, mammalian cells, and insect cells. So you have not these drawback like for the nickel NTA resin. Here you can see the picture from before and the comparison with the streptactine XT resin. Here the pink fluorescent protein M-cherry was tagged with the twin strep tag and purified with the streptactine XT high capacity resin. And here the protein directly bound to the resin after application and do not flow through, because the binding of the twin strep tag protein is not influenced by the supplements of the media. So these free amino acids or biotin do not influence the binding of the twin strep tag protein to the streptactine XT resin. So the binding between the ligand streptactine XT and the twin strep tag is really tightly, and you will not lose your protein during the application and washing. Yeah, and the purity, a further requirement for protein for structural analysis, is really high with the twin strep tag and the strep tag too. Here you can see the proteins from before, M-cherry and GAPDH, and both are tagged with the twin strep tag and purified with the twin streptactine XT resin. You can see the flow through and 3 elution fractions. And in comparison to the his-tag purification, there are no other proteins or unspecific bound proteins, and the purity is really high with more than 95%. So you do not need to optimize the purification condition independent of your target protein, and we always still have a high purity if you take the strep tag 2 or twin strep tag. So as for the his-tag based protein purification, you have 4 steps for your purification. You have the equilibration step, the sample application, and the washing step and elution step. And you have not to optimize these wash step and elution step, because for each protein you can take the same protocol and have not to do optimization steps, and so you will be faster and it will be more simple for you if you take the twin strep tag or the strep tag 2. So the last property or requirements which should be fulfilled for structural analysis are the folding of the protein. And yes, you will have naturally folded protein if you take these tags. And you can use various buffer compositions and adjust the buffer to your target protein. Because you can add, if you have a cytoplasmic protein with cysteines, reducing agents like DDT or TSAP, and you can protect your proteins from unnatural disulfide bonds. And if your protein is prone to oxidation, you can also add reducing agent, because the stability or the binding capacity of the twin strep tag resin or strep tag 2 resin is not influenced by reducing agents. And the addition of chelating agents is also possible. You can add EDTA and EGTA. And so your protein is protected for proteolytic damage. And the last components I would like to mention are tris, TAPs, MOPs, and ammonium. And you can also protect your protein if it is very pH sensitive. and you can take the buffer which is the best one for your target protein. So I would recommend to take the strep tag or a twin strep tag if you plan structural analysis. And now we come to the last question of this webinar. Which resin format should I choose? So it is possible to take magnetic beads, pre-packed gravity columns, or HPLC or FPLC cartridges. I would take cartridges if you have a system for automation, for example, an actor system, because these cartridges are really easy to handle, and you can put this in the HPLC, FPLC, and it works from alone. But if you do not have a system for automation, gravity flow columns or magnetic beads are applicable as well. So this slide should show you how often, or not show only show that the strep tag is often used for in combination with cryo-AM or structural analysis. And these references are more or less all from 2020 from this year. And there are several references more. And if you're interested, you can contact us, and I can show you more references. And with this, I want to sum up or conclude. So the first question was, which expression host should I choose? And the take-home message is choose a host that is similar to the original organism and consider signal sequences. And the second question was, which buffer system should I choose? And therefore, I would recommend take a buffer system that fits for your protein and your application. And for the affinity tag, I would recommend to use the most flexible tag, so the strep tag 2 or twin strep tag. And for the resin format, you can use a resin format which provides the required amount, for example, columns, cartridges, or mostly also magnetic beads. Yeah, and with this, I would like to finish my presentation, and now we have time for questions.